All right, guys. So, right now, if you can go into Schoology, go to your class notes, and you're going to take the assignment for today, which is basically just open it up, grab the notes for 1.6, and I want you to import them into Notability and add those notes to your Chapter 1 notes. Right now, if you're looking around, you're not really sure, maybe look to the person next to you or behind you. Maybe they can give you a little guidance. If you can't figure out how to attach it to a note, I can help you do that tomorrow. But for right now, let's get the notes into Notability as the priority. And by now, we should be pretty good. So, if I can have your attention, we're going to go through these slides. There are 6 of them for today, and I'm going to give you guys a little time to fill things in as we go. But this first one, right off the bat, a first glance at the Earth's interior. I know that we talked a little bit about Earth's interior and you did the vocab, so you should understand that the inner core is going to be a solid iron and nickel, surrounded by an outer core that is liquid iron and nickel. I'll remind you that that generates Earth's magnetic field and really is the heat source now that's going to radiate out into the mantle, which gives that mantle different properties, and we're going to get into that in chapter 2 when we look at plate tectonics and really how we understand the changing of the earth. And then lastly, after the mantle, you're going to have the crust, and the crust is going to be brittle, it's going to be rigid. The crust is the thinnest part of the earth, and it's the part that we actually live on. So we'll see that in these notes. But just to put it into perspective, from where you're sitting right now to the center of the earth, we're talking over 6,000 kilometers, so 6,371 kilometers. Now that's the average number. Obviously, if any of you decide to climb to the top of Everest, that number is going to go up a little. All right, now let's get right off this slide and into the next one. So I said there was, now we're at number 2, so we're moving pretty quick. All right, how do you know what's inside the earth? See, we've never drilled past the crust, right? No rock have we been able to go and actually collect from the mantle or from the core. So, how do we actually understand what's in there? The first step is that we just study igneous rocks, right? We look at the composition, we use them, and I explained this at the beginning of the year that rocks are like a storybook, right? If we can read the rocks, if we can understand the way that they form, if we can understand the temperatures at which these different rocks are going to form, we can learn a lot about what's going on inside the earth. Then we want to go and take a look at other material in space that would be able to give us clues. So that's where we look at asteroid fragments, we look at meteorites, we've looked at rocks from the moon, all these different examples of material that formed pretty much at the same time that the Earth formed, right? Remember, 4.6 billion years ago. So we're looking at material that all formed around the same time. Chances are we can get a better sense. And from doing that, looking at other planets, looking at the materials, calculating the densities of different materials, we've been able to figure out that if the crust is rich in things like quartz, feldspar, pretty low density. Most the average number for the continent would actually be about 2.7 grams per centimeter cubed. Then we look at the other materials that other planets have, and it starts to make sense that we must have denser material as we move inward. So as you sink further and further into the Earth, the density of the materials have to get heavier and heavier. So from those clues, we are going to be able to figure out that the mantle now is going to be a slightly higher density. We're getting into like the 3 to 7 range in grams per centimeter cubed, depending on which port you're looking at. And then when we get all the way down to the inner core, it's believed that we're up over 13 grams per centimeter cubed. So the density gets considerable, and from that we've also pieced together that we have the liquid nickel and iron outer core, and then the solid iron nickel inner core. Remember, under a lot of pressure, which is why you have that solid, even though it's a higher temperature. So, to recap, right, we study our rocks, we study material from space, we examine the asteroids that land on Earth as meteorites, and then we also conduct experiments, make calculations, build these different models to help us to understand what's going on inside the Earth. All right, almost halfway there, right? Slide number 3, seismic waves. Now, geologists measure the speed and the path of a seismic wave to better understand what's going on inside the Earth. Now, what the heck does that mean? Well, first off, a seismic wave is nothing more than a vibration that's going to pass through the Earth. We have seismic waves that travel through the Earth. We call them body waves. And those are your P waves and your S waves, your primary waves and secondary waves. And then we have our surface waves, which are referred to as Rayleigh waves, Rayleigh, right? Rayleigh waves, and love waves. Hopefully I don't have to spell that one for you. So these waves tell us a lot about the materials inside the Earth. And in particular, the body waves, when they pass through the Earth, are going to refract. Basically, they're going to bend as they travel through different materials. And when they study the wave path, they were actually able to figure out that the P waves were able to come down, right? So they're passing through the Earth, right? Imagine right now you take your hand, you're imagining that you're moving down through the Earth, right? But you're curving ever so slightly. And when it changes a material, there's going to be a little bit of a bend, and then another bend when it changes to a different material. So think about, I'm saying material, you're talking about a brittle or rigid crust, then you're going to a ductile outer core. Then we're going to actually transition at one point in the mantle, but then skip that part. You hit the liquid outer core. That's going to be a substantial change. The wave is going to have to react, and the P wave can do this. P wave can do this because it's a compressional wave. It keeps driving in the same direction that the wave has been traveling. So it hits the liquid, it's going to bend. Maybe it hits the solid inner core and speeds up. Now it hits another liquid layer on the other side, again bending drastically, and then pops back out. So P waves can pass all the way through the center of the Earth. By contrast, you have this S wave that we were talking about, right? The secondary wave, or also known as a shear wave. This wave is going to travel perpendicular to the wave path. So as it's moving, right, it's kind of wanting to go side to side as it's getting there, zigzagging, if you can picture that. I apologize, I can't scribble it on. Actually, maybe I can. So, P waves, right, just keep moving in the same direction, right? So this is your P wave. Your S wave, on the other hand, wants to do this. It wants to zigzag as it's going. So yes, in the big picture, it is driving down this way. But as it's zigzagging, right, it's going to move a lot slower. Kind of like if somebody wanted to get down the hall, right, and they want to move with purpose, they're going to walk straight down the hallway. They're going to go from A to B in the shortest period of time. But for the person that wants to zigzag down the hallway, right, they want to stop in, oh, hi, Mr. Kennedy. Oh, hi, Mrs. This one, that one, right? As they bounce side to side down the hallway, it takes them a lot longer. So in the same way, the S wave is that side to side wave. Now, why am I explaining all this? Because when an S wave hits a liquid, right, in the sense of the liquid outer core, the wave actually kind of just dissipates. It gets lost because it's going to move sideways in a fluid. So imagine like you trying to move through water and you're trying to move side to side. Well, now you're going to get swished all over the place. And sure enough, S waves stop when they hit the liquid outer core. If you're on the other side, right? So here, I'm going to draw a little earth. All right, I got to find a better way to do this. Here we go. Right, if you're on the other side of the earth, and this right here is the inner core, well, when your S wave's coming through, right, it stops. When your P wave comes through, right, it's going to bend, keep coming. So if I have a seismograph, which we're going to learn about later on, seismogram, you get the written record, we call it a seismograph. You'll have the P wave arrive, right, and it looks like this. But then there's no S wave. And this helps scientists to figure out that the outer core, in fact, was liquid and then the inner core was solid. Don't worry, we'll have a whole chapter where we focus on this, but I figured why not break into it. All right, now, the crust. The crust, I think of the layers of the earth like a pizza. And, let me specify to the purists in the room, like a Neapolitan pizza. That's the round pizza. And when you think about that, the crust that you hold on to is always brittle and rigid. And that's why you pick the piece up and you can snap it, right? And you get that nice little sharp handle. And then you chomp down. Well, Earth's crust is the same idea. It is brittle, it is rigid, it will snap. You're not going to really be able to bend it. And this is because it's made up of cooled rock, very old rock. By contrast, underneath you might actually have molten rock, so that's not even, it theoretically hasn't been born, if you think about it. Now, what do we have here? Earth's crust, made up of rocks. The continental crust is rich in granites, feldspars, quartz, an average density of 2.7 grams per centimeter cubed. All right, I'm going to reiterate that. The crust for the continental crust is going to have a density of 2.7 grams per centimeter cubed. It's also going to be much, much older than the oceanic crust. It's also going to be a lot thicker, and you can see that in this picture right here. You can see that the mountains are very, very big. And note that as the mountains go up, you also get this root over here that goes down because there's what we call an isostatic rebound. As you build up, you also have to push down because the crust, while it's rigid, is floating on this ductile asthenosphere, this ductile upper mantle. So we'll get into that. But the separation between the crust and the mantle is called the MOHO, or the Mohorovic discontinuity. I'll say it again. Mohorovic discontinuity. Just in case you guys want to look it up and understand it a little bit further. Now, over on the right-hand side, you have the oceanic crust. And the oceanic crust is going to be a lot thinner. It's going to be more dense. And it's also going to be much younger. Now, we said that the Earth is 4.6 billion years old. We could get in a school bus, and within a day, we could drive up to the Canadian Shield, and we can look at rocks that are over 4 billion years old. But if we got in a boat and traveled all around the world, you cannot find oceanic crust that is any older than 180, wait for it, million years. 180 million years. So by contrast, all oceanic crust is much, much younger than continental crust. So these are themes you're going to need to look back on throughout your time in Earth science. Again, next chapter we're going to get through a bunch of detail on it, but I just want to paint this picture for you now. All right, so now we're up to the mantle, the largest part of the Earth, right? Rich in peridotite, and while it's very thick, was really not a lot of activity that we're going to focus on in the mantle. The most important part is that you understand that it sits below the crust, that the uppermost part of the mantle is called the asthenosphere. The asthenosphere is going to be ductile. I use the analogy that it's like hot cheese, where it's not solid, but it's not liquid. Right? So it's ductile, it's the semi-solid, and it allows for the crust and the lithosphere, the crust plus the uppermost brittle mantle. It allows it to float on top of that, and it's going to be a critical concept in plate tectonics. And then the core. Now I apologize. I'll say this again because it can't be said enough. The core is the innermost layer of the Earth, made of iron and nickel, and divided into the liquid outer core and the solid inner core. So that's that definition that you're going to be looking for tomorrow when you have your vocab quiz. So what I want you guys to do right now is take the rest of class time and just go over your vocab, read up on any points that we may have touched on in the notes, and I hope you guys have a great day. Study for your quiz tomorrow. That is your homework. To the sub that's covering my class, thank you so much for taking the time today. I hope you enjoyed the lesson. Have a good day.